Can a line separate apples from oranges on a table? In machine learning, that simple question is the heart of a powerful idea, the support vector machine. I'm Aarav-X. In the next few minutes, you'll learn what an SVM is, how it uses a hyperplane to separate data, what support vectors are, how the kernel trick solves nonlinear problems, and where SVMs are used in the real world. A support vector machine is a supervised learning method used mainly for classification. In simple terms, given labeled examples, it looks for the best boundary that separates classes. That boundary is called a hyperplane. Picture many possible lines that separate apples and oranges. SVM picks the one that maximizes the margin, the distance between the line and the nearest examples from each side. That margin makes the classifier robust. New points near the boundary are handled more reliably. The points closest to the hyperplane are the support vectors. They define the boundary. Support vectors are the data points that matter. If every other point disappeared, the support vectors alone would still give you the same hyperplane. That's why SVMs can be very efficient. They summarize the decision using only a few examples. But what if a straight line won't separate the classes? Enter the kernel trick. Instead of forcing a line in the original space, SVMs map data into a higher dimensional space where separation is possible. Think of lifting apples and oranges into 3D where a flat plane now splits them cleanly. Kernels, like polynomial or radial basis functions, provide that mapping implicitly. You don't compute the coordinates in high-dimensional space directly. You use a kernel function that measures similarity. In practice, data can be noisy. SVMs use a soft margin, allowing some misclassifications to avoid overfitting. A parameter called C balances margin width versus classification errors. Tight margin, fewer errors, or wider margin, more tolerance? It's a trade-off. With a low C value, the SVM algorithm is more tolerant of misclassifications. It prioritizes a wider margin, even if it means some data points are on the wrong side of the boundary or within the margin. This can lead to a simpler model that generalizes better. With a medium C value, the model strikes a balance. It penalizes misclassifications more than a low C value, leading to a narrower margin and fewer noisy points crossing the boundary. A high C value makes the SVM very strict. It aims to correctly classify all training points, resulting in a very narrow margin. This can lead to a complex model that is prone to overfitting the training data. Where are SVMs used? Classic examples include email spam detection and image recognition. For spam, features like word frequencies, sender reputation, and links produce a vector for each email. An SVM learns a boundary that separates spam from legit mail, often using kernels to catch complex patterns. Quick takeaways. SVMs are powerful when you have medium-sized datasets, clear margins, and need robust decision boundaries. But they can be slow on very large datasets and less interpretable than simple linear models. Also, choosing the right kernel and tuning parameters takes care. So, SVM finds the optimal boundary, uses support vectors to define it, and the kernel trick lets it separate nonlinear data. If you want, next video I'll show step-by-step code, a simple SVM in Python, kernel comparison, and practical tips for tuning. Which kernel should we demo first, radial or polynomial? Tell me in the comments. Subscribe to Pixelsface AI for clear, calm explanations of core machine learning ideas. I'm Aarav-X. See you in the next lesson.